Hey everyone, thanks for watching. In this video, I just want to go over the summer project that I've been working on. It's called battery leveling. So I'm in this club called AirVP, and then we make this this underwater robot. And since I was away from the club, I didn't have much to do. So I kind of gave myself this task of remaking this battery leveling board. And one thing I ran into was there was three ways that they kind of proposed to make the board with, but then they ended up going with this Power Mux thing, which is like probably the easiest implementation, versus either having diodes or the NMOS controller, the high side NMOS switch controller. So what I wanted to do with this document is kind of do the simulation um, for each of the different ways you can do the battery leveling and see which one comes out first. Because I asked the team members, and like there was still like people were kind of uncertain about which one to do, but I just wanted to simulate either way. So here's like the daily. So I'll just go over the doc, how to read the doc if you ever want to check it out. So the daily log is like whatever I put in it. So like whatever I did that day, it's in there. And then this is like the initial introduction, like what is the purpose, like my understanding of the current implementation right now, and then the different simulations that I want to run, and then this I'll go into after. But on the bottom here, uh, this might be, I might have to move this one up, but it's like the AirVP specs and requirements of like what the what the bot actually does and what we want this board like the voltages and the amps that the battery is kind of like supplying, and then these are all the components in the previous one. So the idea was I was going to populate what the component was in there, but like this is a very a very basic explanation, so like I'm not going to do that. So let's just jump into it here, and then sorry, if you go all the way down, here's the general like quick link. So like I tried to make this as like accessible as possible. So like if you didn't know like any sort of like electrical engineering, but you still wanted to follow along, you can like these are all like the basic things that like I kind of picked up and like we kind of learn in class. So I just put that there so everyone can know. Um, but if we go up here, we'll just start with the simulation, like the degree to which we can simulate the battery. So as far as I know, and I may be fully wrong about everything here, is that like there's a very crude simulation that we can run, and then actually like a very like high level, not a high level, like a very specific one, and I'm fully aware that like I'm not capable of making the fully like the nitty gritty simulation. It might be worth to just like make the board itself and see and run tests on it. So the initial idea was to run the three simulations within MATLAB. So I started with MATLAB and I tried to figure out like how to use it, but it was extremely hard. So I kind of gave up midway. I'll show you. So the MATLAB information is right here, and then it never went past this. But if you want to check out the documentation, there's a bunch of things you can use with the Simulink. Um, Frankly, it's just so overwhelming that I couldn't even get started. So I decided to use something called LT Spice, which is like another like simulating software. So you can sort of easily make simulations with this. It's really straightforward, and like it's easy to use. You can put in blocks, you can add wires, and like there's not much. It's you can sort of pick it up as you go. Um, but so the initial, what I wanted to do is simulate the battery, like the actual power efficiency of like the voltage drops, the amps, everything's coming in, and then after that do the thermal the thermal loss. So then we could see like if we're like losing power due to thermal constraints as well, since everything like probably does need to be cooled, right? So um, so the way I approach this is first simulating the battery and the load, and then adding the implementation of the diodes and the NMOS, the bootstrap circuit, and the power mux. So the battery simulation, the battery we're using right now, if you scroll all the way down here, it's called the 4S2P. So it's a lithium ion battery with a max 6.8 volts. So the arrangement of that is, you can kind of see it here. So it'll be 4 strings. It'll be 2 strings with 4.2 volts across it. So each string is gonna have, so if this is 1, 2, 3, 4, each of them is gonna have 16.8 and then 16.8 on the other side as well. So that's where the primary concern with like the whole like battery leveling issue comes into play. So what happens when, so the issue is each cell that you get from the manufacturer doesn't have to be exactly 4.2, like each individual cell that adds up to 16.8 doesn't have to exactly be 4.2. It can be like, for example, here it's 4.17, 4.199, like it could be whatever, and there's like series resistance within it as well. So what happens when you add voltage in series, so let's say I have a 4 volt and a 4 volt, it combines into an 8 volt. So there's no issue there, right? But then if we're combining these two strings, so like I have 4 volts here and then 4.1 volts here, voltage, it always goes from high to low. So there's going to be a current discharge going through. So if I take this 4 volt and this 4.2 volts and I connect it, there's going to be a discharge going into here, and that'll damage the battery, and then that's a no-go. Like it'll actually like burn the battery, so we can't have that at all. So that's why we have this thing in the first place, and these are just different ways of like charging it and discharging it so that like every single cell is balanced equally. So this is the first battery string here. Second battery string, you can see the voltages here. So the first one's going to be 16.7 and the second one's 16.71. So like you can see there's a voltage difference there. So if we connect the two, there's going to be an issue. So yeah, this will cause a current rush, and then now we're going to look at ways to solve it. This is going into the battery. Okay. So if we go over here, a very quick way, and I'll come back to this, I know it's may be a little confusing. A quick way to solve this issue is put diodes there. So what a diode is I'll open up the diode tab. So in case like you forget, you can always come back to this. I'm not going to explain like the physics behind it. Some of that is in here, and there's a video down here as well if you want to really understand how a diode is. But basically, all a diode does, and there's different types too based on like what you want, but all a diode does is it only lets current go through one way. So let's say we have a 4.2 volt here and a 4 volt here, and if we have a diode here and we connect it through that, it's not going to discharge, it's not going to flow this way, it's only going to flow one way. So that's going to look like this. So it's only, so if you look at the orientation of the diode, it's only allowed to flow out. So both voltages, whatever voltage it is, it's only flowing out. So it'll never flow back into the battery, and so you won't have that issue. So that was like one of the ways that we could have solved it. But a fallback with that is that these diodes, when there's like high current rush, the diodes do inhibit some, it's called reverse current leakage. So they let some current like seep through, and that could be an issue for the battery as well. And then it also heats up, and when it heats up, it gets worse. Let's say we have a 50 current surge going through it, it could heat up, and then it'll cause it to not be as efficient, and then it'll have even less, and it's like a negative flywheel, and then it'll just like, it won't be good, the battery's gonna blow. So we don't want that. But then I realized that I didn't have the state of charge. Like I realized that I'm just using a voltage instead of using an actual battery. So I went back and decided to make a better simulation of how how a battery works, because right now these are just 4.2 volts, and it's like infinitely 4.2 volts. So I wanted to make it so that like the 4.2 volts, you can't get infinite. Like after a while, the voltage goes down and like there's not much current in it. So I did that using a behavioral voltage source. So with the behavioral voltage source in LT Spice, what you can do is you can basically set it to any math function, and then you can use that to like to make voltage whatever you want. So here, like I put in a sine wave just to give you guys an example, but that's how I was going to do it. So I was learning a lot of like new terminology, and then state of charge is one of them. So state of charge is SOC of the battery. So what it is it's going to be the percent of charge you have left. So let's say like you use 10% of your battery, your state of charge is going to be 90%. Pretty straightforward, but the thing is, like I said, the battery pack is at 16.8 the whole time, right? So the thing is, as the state of charge goes down, the voltage inside the battery goes down as well, right? So there's going to be it's not a linear relationship, but there is a relationship between the two, and that's captured through this lookup table here. So what this is it maps 100%. We have 16.8 volts ready to go, and then at 90% we only have 16.4, and then so on and so forth. So that's like it affects like how much voltage we can actually pull, how much current we can pull, how much voltage we have in the actual battery. And then so there's two things that determine how much voltage you can actually you can take, because 16.8 is just the open circuit voltage. So that's like we have 16.8 when like the manufacturer sort of made it, but the actual voltage when we use it is different, and that's based on the first one being state of charge, so how much charge is actually left in the battery, and another one called voltage sag. So voltage sag is how much you're pulling from the battery. So that's given by this equation here. So it's going to be your internal resistance times the current you're pulling. So no matter what load you have, it doesn't matter what load you have, but let's say you have a battery pulling, probably better to do with an example. Yeah, sorry, there's technical difficulties, but I'm just gonna jump in right where we left off with what SOC is and how voltage sag works. So basically that's how much voltage the load is actually pulling in from the battery. So we can do a simulation right here. So right now I'm pulling in 5 amps, right? So I'm gonna run the simulation, and then it's gonna be around that 16.5 mark. But then the voltage sag goes up when I'm pulling, like let's say I'm pulling 20 amps, and I run the simulation again, and it's going to 15.8, right? And the reason that happens is because we need to account for the resistance, for the internal resistance within the battery. And like that's just like something like an ideal battery won't have any resistance, but in like real world applications we do need to factor in an internal resistance. But yeah, that's kind of it. There's some more information here that I'm gonna go through after, but yeah, thanks for watching, guys. And if you have any questions, feel free to ask. Like I'm always here to help. And if you have any corrections too, like I'm pretty open to that too. Okay, awesome. Thank you so much.